After understanding the idea and concept behind the mathematical induction through examples, namely infinite ladder and the infinite sequence of dominoes, learning the principle of mathematical induction, and proving the validity of mathematical induction from previous video, now it is time for us to enter into the second part, that is solving the problems using proof by mathematical induction. In this slide, let us prove the summation formula. Here one thing you keep in mind, for all the problems, P of n will be the propositional function, which have to be proved true for all values of n. Now let us consider this problem. Here the summation 1 plus 2 plus so on up to n is equal to n into n plus 1 by 2. This we have to prove it. As per the mathematical induction, we have two steps, basis step and inductive step. In the basis step, we'll prove it true for P of 1, since 1 into 1 plus 1 by 2 is equal to 1. Hence it holds for P of 1. In the inductive step, we assume it is true for P of k. So the inductive hypothesis will be 1 plus 2 plus so on up to k is equal to k into k plus 1 by 2. With this assumption, now we have to prove it for P of k plus 1. For that, we'll write the summation as 1 plus 2 plus so on up to k plus k plus 1. Now 1 to k, sum will be replaced with k into k plus 1 by 2. Then we'll have plus k plus 1. After solving this, you'll have the equation k into k plus 1 plus 2 into k plus 1 by 2. Now you take k plus 1 common, then you'll have the resultant equation k plus 1 into k plus 2 by 2. This is true for P of k plus 1 because when you substitute k plus 1 in the place of n in the above equation, n into n plus 1 by 2, the following results. Hence, this is proved for all values of n. The problem is conjecture and prove a correct formula for the sum of the first n positive odd integers. When you observe the problem statement, we have two phases here. First one is conjecturing and second is proving. First, let us understand what do you mean by conjecture. It is a process of coming to a conclusion or inference based on incomplete information. So based on this, first we have to formulate for the sum of the first n positive odd integers. Let us do it. Now let us take the n values from 1 to 5. When n is equal to 1, we got the sum as 1. When n is equal to 2, 1 plus 3 is equal to 4. When n is equal to 3, 1 plus 3 plus 5 is equal to 9. When it is 4, the sum is 16, and when it is 5, the sum is 25. When you observe the sums, the sum is equal to n square. Now, what could be the nth term? When n is equal to 1, it is 1. When n is equal to 2, it is 3. When n is equal to 3, it is 5. So on, when n is equal to 5, it is 9. So the nth term could be 2n minus 1. From the above examples, we can conjecture that the sum of the first n positive odd integers is n square. That is 1 plus 3 plus 5 plus so on up to 2n minus 1 is equal to n square. After conjuncturing the formula, now it is our turn to prove the conjecture whatever we obtained using mathematical induction. Here the basic step will be P of 1 is true because 1 square is equal to 1. For the inductive step, we have to prove that P of k leads to P of k plus 1 for every positive integer k. Here the inductive hypothesis is 1 plus 3 plus 5 plus up to 2k minus 1 is equal to k square, which we have assumed to be true. With this assumption, now let us show that it holds for even P of k plus 1. That is, the sum 1 plus 3 plus 5 plus so on up to 2k minus 1 plus 2k plus 1 is equal to k minus 1 square. In this, the sum 1 to 2k minus 1 can be replaced with k square. So finally it becomes k square plus 2k plus 1 which is equal to k plus 1 square. Hence it is proved for P of k plus 1 that it follows from P of k. Therefore, it is proved that the sum of first n positive odd integers is n square for all values of n. After proving summations, mathematical induction can be used to prove various inequalities that hold for all positive integers greater than a particular positive integer. Now the problem is use mathematical induction to prove that n less than 2 to the power of n for all positive integers n. Let P of n be the propositional function that n is less than 2 to the power of n. In the basis step, since 1 is less than 2 to the power of 1 is equal to 2, P of 1 holds. In the inductive step, let us assume that it holds for P of k. That is, k is less than 2 to the power of k for an arbitrary positive integer k. Now we have to prove that it holds for P of k plus 1. For k less than 2 to the power of k, add both sides 1, which results in k plus 1 less than 2 to the power of k plus 1. Since 1 is less than or equal to 2 to the power of k, 1 can be replaced with 2 to the power of k. Now it becomes 2 to the power of k plus 2 to the power of k, which is equal to 2 into 2 to the power of k, which in turn equals to 2 to the power of k plus 1. So it is proved for P of k plus 1. Hence, it also holds for all positive integers n that n is less than 2 to the power of n. Now let us take one more inequality problem. Use mathematical induction to prove that 2 to the power of n less than n factorial for every integer n greater than or equal to 4. Here we start the basis step at P of 4 because the propositional P of n will be false for the values n less than 4. Let us verify it by checking P of 1. 2 to the power of 1 less than 1 factorial. 2 to the power of 1 will be 2 and 1 factorial will be 1. 2 less than 1 will be false. Let us check with P of 3. 2 cube less than 3 factorial. 2 cube will be 8. 3 factorial is 6. 8 less than 6 is also false. Hence, we start our basis step with P of 4. Since 2 to the power of 4 is equal to 16 and 4 factorial is equal to 24, 16 less than 24 is true and P of 4 holds. In the inductive step, let us assume that it holds for P of k, that is 2 to the power of k is less than k factorial for a arbitrary integer k greater than or equal to 4. Now we have to prove that it holds for P of k plus 1. 2 to the power of k plus 1, let us write it as 2 into 2 to the power of k. 2 to the power of k is less than k factorial. So 2 to the power of k can be replaced with k factorial and it becomes less than 2 into k factorial. Since 2 is less than k plus 1, 2 can be replaced with k plus 1. So it becomes less than k plus 1 into k factorial, which is equal to k plus 1 factorial. So 2 to the power of k plus 1 will be less than k plus 1 factorial. Hence it is proved for P of k plus 1. Therefore, it also holds for every integer n greater than or equal to 4, that is 2 to the power of n will be less than n factorial. Here, we use mathematical induction to prove divisibility results about integers. Usually, these results are proved using number theory principles. Let us get into the problem statement. Use mathematical induction to prove that n cubed minus n is divisible by 3 for every positive integer n. Here also we take P of n as the propositional function that n cubed minus n is divisible by 3. In the basis step, since 1 cubed minus 1 is equal to 0, which is divisible by 3, P of 1 holds. In inductive step, we assume that it is true for P of k. That is, k cubed minus k is divisible by 3 for an arbitrary positive integer k. Now we have to prove it for P of k plus 1. Now you replace n with k plus 1. We'll be having k plus 1 cube minus k plus 1. Expand it, you'll have k cube plus 3k square plus 3k plus 1 minus k plus 1. When you rearrange it, it will be k cube minus k plus 3 into k square plus k. The first term k cube minus k is already divisible by 3 by the inductive hypothesis. The second term 3 into k square plus k is divisible by 3 because it is an integer multiplied by 3. Hence, k plus 1 cube minus k plus 1 is divisible by 3. That is, P of k plus 1 holds. Therefore, it is true for every positive integer n that n cube minus n is divisible by 3. Hence, it is proved